today we shall consider the most general type of a machine, Turing machine. We have already considered finite state automata which corresponded to type 3 grammars, and also we have considered the push down automata which was equivalent to type 2, and we have studied 4 types of grammar, the Chomskyan hierarchy, type 0 and type 1. The Turing machine corresponds to type 0 grammar. The equivalence we shall study later is a machine model. The machine model was defined by A.M. Turing in 1936, and he called the basic model as a computer. He just called it as a computer. And what he stated is this: what could naturally called an effective procedure can be realized by a Turing machine. This is known as Church-Turing hypothesis. Now, what he did is he constructed an abstract model, and that abstract model had an infinite tape. Turing machine has an infinite tape which is divided into cells. It is infinite. You can take it infinite in both direction or in one direction, does not matter. Later on we will see the equivalence between these two things. Except for some portion, some A1, A2, AN, the rest of them will be blanks. I will denote the blank portion with a B and a slash. Except for a finite portion, the rest of them will be blanks. The tape is infinite, but the non-blank portion is only finite. Now, you can look at a Turing machine as an input-output device or an accepting device. When you look at it as an accepting device, it accepts type 0 languages. First, we shall look at it as an input-output device. And what is the input? The input is the non-blank portion when you start the machine. How does the machine work? Depending on a state and a symbol. The current state is Q and the symbol read is A. The next instance, the state can change to P, and this symbol will be read, and you can rewrite over that symbol. Something else will be written on that cell, and then the tape head can move right or left. It can move right or it can move left. There are some symbols which can be written on the tape. They are called tape symbols. Gamma, if you denote as tape symbols. The mappings will be written like this: delta of QA is equal to P A R, something like this. Formal definition I will write in a moment. This means that in state Q, if you are reading A, each cell contains one symbol. So, if you are reading A from Q, you will go to state P, instead of small a you print a capital A and move right. Okay? And what he proved, that you can compute anything. At the end it will go to halting state and halt, and when the machine halts, whatever is the non-blank portion, that is the output. Whenever you start the machine, the non-blank portion is the input, and after some move the machine will go to a state called halting state. It will start some of the states, it will just halt. So, when it goes to halting state, whatever is the non-blank portion, that is the output. So, you can look at it as a input output device. Now, what Turing said in 1936 was that whatever could naturally be called an effective procedure can be realized by a Turing machine. What is an effective procedure? An effective procedure is like a program. It tells you what is the next step to be performed. If it is not some line of the code is there, next line it will be executed, next line, and if there is a transfer of control, you can use a go to, or here itself if then else you may use some portions where the code control will be transferred. In essence, it tells you what is the next, what you have to do in the next step. Okay. That is an effective procedure. Usually the words procedure and algorithm, they are used with the same meaning or something like that, but there is a slight difference between them, a procedure and an algorithm. What is a procedure and what is an algorithm? Essentially they are programs. A procedure is like a program, it tells you what is the next step to be done, right, step by step, doing something in step by step. But what is the difference between algorithm is also like that, isn't it? Step by step you know what to do to solve some problem. But what is the difference between them? The difference between them is that a procedure can halt or need not halt. An algorithm is supposed to always halt and give you the answer. An algorithm, at the end you are supposed to get the answer for your problem. In a procedure, if the answer is yes, you may get, if the answer is no, you may not get the answer. I will tell you with an example which will illustrate you a better manner. The input is a natural number. The problem is it a prime? You are going to test, given input is a natural number and you have to test whether it is a prime or not. If we let us not worry about effective, time and all that, the efficiency of the algorithm, just look at something which could be solved. Then how will you find out whether a number is prime or not? Try to divide it by 2. The remainder is 0, it is not a prime. If the remainder is not, if the remainder is 0, it is not a prime. If the remainder is 0, try with 3 and so on, isn't it? That is the way you proceed up to p minus 1. If the input is p, up to p minus 1 you will try. In fact, you can try up to root p, that is a different thing. But at the end you will be able to say whether the given number is a prime or not. Definitely there is an answer. Is it a prime or not? It is a prime means you will say yes, it is not a prime, no. So, that is an algorithm, you will definitely have an answer. Whereas, look at another problem. First problem which we considered is given n is n a prime, this one. given n, is there a perfect number given a number n, is there a perfect number greater than n? What is a perfect number? The sum of the devices is sum of the devices is equal to, for example, if you take 6, 1 plus 2 plus 3 will give you 6, the devices are like that. If you take 28, the devices are 1 you have to take 1, 2, 4, 7, right. 28 is a perfect number. But given a number n, is there a perfect number greater than? We can always test, given a number n, you can test whether it is a perfect number or not. That, see, you can find all the divisors, then add them up, is it equal to the number? So, given a number, is it a perfect number or not, you can test, right. Given a number n, is there a perfect number greater than n? That is the question. Now, what will you do? You can write a step by step procedure like this. Take n plus 1, find out whether it is a perfect number or not. If it is a perfect number, yes, otherwise you will take n plus 2, right. Try for n plus 2. If it is not a perfect number, take n plus 3. If it is not, take n plus 4. If it is not, n plus 5. So, if the answer is yes, ultimately you will come out with a yes answer. But if the answer is no, you will keep on trying the next number, you will not know, right. But this also you can write step by step a program for this. I is equal to I plus 1, test whether I is a prime, I is a perfect number. If not, again go back, I is equal to I plus 1, test whether it is a perfect number. You can write a step by step procedure, but if the answer is yes, it halts, if the answer is no, it goes on trying. That is also an effective procedure, right. But it may halt, that is the slight difference between a procedure and algorithm, which may not be mentioned very clearly in many books, and many books may use procedure and algorithm in the same manner. But this is the difference. As a Turing machine, and when you study halting problem and all that, this difference will come out. Okay. So, the number, you can look at it as a input output device. What is given initially is the input, the non-blank portion, and when you halt, what is given is the output. If it is not going to halt, it is going on for ever in a loop, right. Now, initially you may have some number, and ultimately you may end up with another number. For example, you may have something like this. You may have a number n, it is not in one cell, some number, say 5, binary or decimal you can have, does not matter, 6, another number m and n, and you may write the Turing machine so that ultimately you come up with m plus n or multiplication m into n and so on. So, it is computing a function from the set of non-negative integers to non-negative integers. We can also look at it like this. So, given n, initially some number, here there are two numbers. So, actually it will be n cross n, from n cross n to n cross n, right. Anyway, from natural numbers, depending upon the arguments, it is computing a function, right. Now, can you compute anything with this? you cannot compute. There are things which cannot be computed by the computer or current day computer or with the Turing machine. The set of computable functions, there are functions which are not computable. Why? Because the set of functions itself, from natural numbers to natural numbers if you take, that itself is uncountable. Whereas the number of Turing machines are the number of effective procedures. If you make one Turing machine correspond with one effective procedure, that is countable. One will correspond to something like a real number, another will be natural numbers, and you know that they cannot be put to one correspondence, right. That is what yes. That shows the existence of things which cannot be computed. Okay. So, for example, take like this. How do you know that there are functions which cannot be computed, uncomputable functions? For just simple, take from all functions from n to 0 1, set of non-negative integers to 0 1. I can represent it as a real number. For example, 0 goes to say 1, 1 goes to 1, 2 goes to 0, 3 goes to 1, like that, something. One function. This you can represent as, say, for example, 0.1101, like this. It is a real number, right. So, if you look at all functions from n to 0 1, you can make them correspond to, say, real numbers, and you know that the set of real numbers is uncountable. But the number of Turing machines or the number of effective, any Turing machine you can describe in a proper way, like 6 tuple will use k sigma gamma delta q naught f or whatever it is, that you can write as a string over some alphabet, and strings over an alphabet in the standard representation, you have lexicographic ordering and standard ordering, which we studied. Lexicographic ordering, I mean, it is not a well, in the sense that there may be elements which comes prior to that and you cannot define, but standard ordering you can enumerate the strings, any alphabet you can enumerate the strings over that. This argument we are going to study again and again, that is why I always keep mentioning that you should not miss the class, because whatever we say in one class, it will be carried on to the next class, and if you miss the classes, you may not be able to follow what is said in the next class. Okay. So, what happens is, this functions you can make them correspond to a set of real numbers, whereas the procedures, effective procedures, you can describe as a Turing machine, and the Turing machine can be represented as a string, some string representation you can give over some particular alphabet, and any over particular alphabet the strings are enumerable, you can enumerate them. So, they correspond to, when something is countable, it corresponds to a set of natural numbers. So, you cannot have a one-to-one correspondence or some correspondence between real numbers and natural numbers. So, there are functions which could not be computed by some effective procedures. So, there are uncomputable functions. Now, I used to say for example, can you do anything with a computer? There are certain things which you cannot do with a computer. For example, if I say you want to list all the simple sentences in English, meaningful simple sentences in English, you cannot do that, because that meaningful is there. You cannot write a program to do that, right. What the computer can do, only if you can write a program for that. If you are not able to write the program, you cannot do that, right. So, another function which is not computable, I will give an example. If you are not able to follow this at this moment. Do not worry, I will come to that again after 2-3 classes. You start with a infinite tape, a Turing machine with blank symbols, whole tape is blank, and you have a Turing machine with n states. You can have n states. You start the machine anywhere you want. It should print once and ultimately halt. There may be several Turing machines like that with n states. It should print some ones on the tape and then ultimately halt. Please remember that. You can have a Turing machine which keeps on printing 1, 1, 1, 1, 1 and going for infinity without stopping, but ultimately this machine has to halt. So, with n states I can have several machines, right. So, what is the maximum number of ones which could be printed on a tape when you start on a blank tape with a Turing machine with n states? That is the question. Suppose I denote it by some f of n. This is called a busy beaver function. It is an uncomputable function. Why it is not uncomputable? During the course, in the next 3 or 4 lectures, after 3 or 4 lectures, we will see why this is not computable. So, there exist functions which cannot be computed. Now, what Turing said is, whatever could naturally be described as an effective procedure can be realized by a Turing machine. So, if you can write something as a program or step by step, you can implement it on a Turing machine. The difference between a Turing machine and the current computer is, Turing machine is not random access, whereas the current thing is random access. So, you talk about register machine or random access machine. This again I will deal with at a later stage in detail, register machine or random access machine. And in another direction you have, this is exactly go and fetch some information, that is what you do in a computer, isn't it. In Turing machine the same thing you can do, but it is divided into cells, and if I want some information from here and I have to get it here, I have to traverse like this, go and get, right. So, that is the only difference, and it has been proved that you can simulate one with the other, time will be only at the most quadratic. If something you can do it in time t, you can do it in time t squared, and something if you can do in time t, here you can do with t squared maximum. So, if something can be done in polynomial time, in the other one model also it can be done in polynomial time. The non-polynomial or polynomial time is not going to be affected which model you consider. So, generally for all computational models people have taken Turing machine for all proofs. Okay. I will, and there are other model, this model of Turing machine, even though it was stated in 1936, all these years it has stood the test of time, and any other model which you define like partial recursive functions or post canonical systems, other things type 0 grammars, any other model people have defined, they were shown to be equivalent to that of Turing machine. Any other model of computation people have defined, it has been shown that it is equivalent to Turing machine. These are known as conventional models of computation, Turing machine, register machine, canonical system, type 0 grammar, partial recursive function. Currently the new trend is you have unconventional models of computing. What are they? DNA computing, membrane computing, molecular peptide computing, quantum computing, these are called unconventional models. Then when you define a new model and try to do something, the experiments also people try to do with quantum computing, DNA computing and so on, but experimentally small things they are trying now. But when you go to a new model, you have to prove that whatever is possible with the original model, it is possible, right. So, you have to show that it is universal, the universal computation is possible, or what you mean by that is whatever you can do with ordinary computer or Turing machine, it is possible. So, generally people try to simulate a Turing machine or in essence type 0 grammar or something like that. So, that is a trend. When you define a new model, you have to show that it has the capability of that of a Turing machine before you proceed further. It is a full model of computation, means it should do that. So, this is a slight deviation. Two things in the first half of 20th century were breakthrough results. One was Gödel's incompleteness theorem. The second is halting problem of the Turing machine. These are two breakthrough results. Because of that, people were able to show that certain things people were trying where you cannot write algorithm for this. For example, given a context free grammar, is it ambiguous or not? It is an undecidable problem, right. And earlier Hilbert posed several problems. One of the problems is called Hilbert's 10th problem, that is, given a polynomial with integer coefficient, does it have integer roots? It may have or it may not have. Can you write an algorithm which will take as input a polynomial with integer coefficient, tell you whether the roots are integer or not? And people tried to write an algorithm for that, they were not successful. But after Turing stated his unsolvability result, it became known that you cannot write an algorithm. I told you it is a very strong statement to say that you cannot write an algorithm, that has to be proved. Okay. So, we will deal with those things after say 4 or 5 classes. Now, coming back and another deviation again to tell you this also, I do not know whether I have told you, A.M. Turing is a British person. Even today there is an award being given in his name, and he has been Turing award lecture people give, a person who does very good work in computer science is being awarded with that. He had his earlier education in South India, Bangalore, Ooty and places like that. So, I always tell the class that you IIT people, you also have your young earlier education in India and you go abroad and do very well. So, for school education or something like that, maybe India is much better than what is given in US. So, let us go to the formal model and consider one or two example. So, it has an initially I will take it as an input output device. You are having a binary number or binary string, I will say, something like that. The rest of it is padded, the tape is padded with blanks. Initially, the Turing machine has a tape and a finite control. It is just similar to finite state automaton. There are two differences. One is the tape is infinite here. Second is you can rewrite a symbol over a symbol read on the tape. So, this machine, it reads this whole thing, and in the first blank symbol it writes a O if the number of ones is odd, if the O and 0 to differentiate, I am writing it like this, if the number of ones is odd, and it writes a E if the number of ones is even. Okay. We had a finite state automaton for this, if you remember. Now, it is going to read and do something here, print something here, O or E. Okay. How will it do? Finite control is again state. So, in state q naught, if it reads a 0, it remains in q naught and prints a x and moves right. The mappings will be like this. We are considering deterministic Turing machines now. Next move is uniquely determined. Non-deterministic Turing machines are also there, we will come to that later. So, what it does is, in state q naught, if it sees a 0, it changes that 0 into a x and moves right in state q naught, right. In state q naught, if it sees a 1, it goes to state q1, right, and prints a x and moves right. I have erased the string, let me keep the original, right, the original string, because you know that ultimately you should get odd, right. This was the original string. Now, in state q1 it reads a 0, in state q1 it reads a 0, it remains in state q1 and moves right. Each time it reads, it is replacing it by x. You can also retain it, you can also retain the input, no problem, slight variation you have to do here. Now, in q1 it sees a 1. When it sees a 1 in q1 state, it goes to q naught. It goes to q naught, changing the symbol by x and moving right. Essentially like a finite state automaton, this is the essence of it, but you are rewriting that as x and then also moving. So, ultimately if the machine is in q naught, what does that mean? It has seen, if it is in q naught, what does that mean? It has seen even number of ones. If it is in q1, it has seen odd number of ones. So, here again in q naught it sees a 1. So, in q1 it will move right, in q1 if it sees a 0, in q1 it will move right. So, the first blank symbol after the input in q1, when it sees a blank symbol, that means it has come across odd number of ones. So, it will halt printing a O. It will go to the halting state and print a O. In q1 if it sees, in q naught if it sees a blank, that means it has seen even number of ones. So, it will halt printing a E. This could be done with a finite state automaton also, right. So, as a Turing machine, how the machine works, this is what we want to know and this can be done. You can also have a sort of a state diagram for this, slightly different from, it is almost like this, but some difference will be there. This I will consider later. So, let us consider one more string which will check the parity of a number. We have already seen that the parity checker has two states, the input alphabet 0 1 and the tape alphabet 0 1 blank and x. The mappings are given as follows. This also we have already seen. Let us consider the string 110101. It has got even number of ones. So, after reading the string it should print a E. Let us see how the machine works on this string. Initially it is reading the symbol 1 in state q0 and we use the mapping delta of q0 1 is equal to q1 XOR. So, the next ID becomes like this. So, it moves one cell to the right, prints a x over the 1 and moves right in state q1. So, whenever it reads a 1, it changes state from q0 to q1 or q1 to q0, but when it reads a 0, it does not change the state. So, from this ID, when it reads a 1 in state q1, it uses the mapping delta of q1 1 is equal to q0 XOR, and the next instance it goes to the next cell reading a 0 in state q0. Next, when it reads 0 in q0, it uses this mapping delta of q0 0 is equal to q0 XOR, and the next ID becomes this. It moves one cell to the right and goes to the next cell in state q0. Because it is reading a 0, it does not change the state. Now, in q0 it reads a 1 and uses the mapping delta of q0 1 is equal to q1 XOR, and the next ID becomes this. Proceeding like this, in the next instance it reads a 0 in q1, uses this mapping, goes to the next cell and then reads the 1 in the next instance, changes the state and goes to the next right cell. So, it reaches the first blank symbol in state q0. If it reaches the first blank symbol in state q0, that means it has encountered an even number of ones. If it has reached this cell in state q1, that means it has encountered an odd number of ones. So, depending upon that, it has to print a E or a O. So, in q0 it sees a blank and uses this mapping and prints a E over this cell, that is over this blank cell it prints a E, which denotes that it has encountered an even number of ones. In that, I will consider one more example, parenthesis checker. Given a string of parenthesis, is it well formed or not? If it is well formed, it will stop printing a y, yes, it will stop printing a y. If it is not well formed, it will stop printing a no, okay, it is not well formed. Let us design the machine for this. So, let me first look at it. The way the machine works, can this be done by a finite state automaton? Can this be done by a finite state automaton? No. Can this be done by a push down automaton? Yes, it can be accepted by a push down automaton. Now, as a Turing machine, how it works? Suppose I have something like this. Is this well formed or not? Is this well formed? It is well formed. So, I also want to have some end marker, this A and A is end marker. Between the end marker, sometimes for convenience I want to have an end marker, right. So, between the end markers, and these are all blanks, the string is given and I have to test whether it is a well formed string or not. Again the machine starts in state q0 reading this symbol. The idea is it moves right and replaces the first right parenthesis by a x and moves left converting the matching left parenthesis into a x. It does it again and again. Ultimately when it reaches there, no more right parentheses are there and it comes back and checks whether there are no more left parentheses, right. So, this is what it does. So, the mappings will be like this: delta of q naught left parenthesis is q naught left parenthesis and right. So, it just moves right in q naught, again the same mapping will be there. Now, it comes here in state q naught. So, q naught is a right moving state, q naught is right moving state. Now, when it sees a right parenthesis in state q naught, what will be the mapping? It changes that into a x and starts moving left. So, it starts moving left in state q1. Now, in q1 it sees a left parenthesis, the matching right parenthesis, matching left parenthesis for the right parenthesis it has converted into a x. So, it changes this into x and moves right in q naught, change again to q naught. So, q1 actually it moves left, it is a left moving state. So, that is q1, I will write for q1 here, delta of q1 left parenthesis is q naught x right. Now, when q naught sees x, it has to just traverse over the x. So, delta of q naught x is equal to q naught x r, it just moves right. So, it moves right and over this left parenthesis also it moves right and here it will change this into a x and starts moving left. Now, in q1 it will encounter this left parenthesis. So, it will change that into a x and move right in q naught, right. So, in q naught it moves right, when it comes here sees a right parenthesis, so it changes that into x and moves in q1. Now, q1 it should move left searching for the matching left parenthesis. So, it has to go through all the x's. So, delta of q1 x is q1 xl, right. Then in q1 when it sees this left parenthesis changes that into x and starts moving in q naught. So, in q naught it will move and change this into x and it will move, and in q1 it will change this into x and again move in q naught. So, in q naught when it is moving it is supposed to see a right parenthesis as long as they are there, but now everything is over. So, in q naught it will see a. What does that mean? All right parentheses are exhausted. So, in q naught if it sees a, it goes to another state q2, it does not do anything with the a, but it starts moving left. Now it should come back here and find out that no more left parentheses are there. So, in Q2 what it does? This is for Q1. In delta of over the excess it has to move left. Q2 is also a left moving state. Q2x is Q2xl, and in Q2 if it sees a that means there are no more left parentheses. It halts saying a yes. Now, if the string is not well formed, it has to say no and halt, right, when there are more right parentheses or so. So, suppose I had one more right parenthesis. So, the machine will be moving here, the Turing machine will be moving here, and in this stage it will print a x and start moving right in state Q1. In Q1 when it is moving left, it is supposed to see a left parenthesis, but instead if it sees a that means the number of left parentheses is less, right. So, in Q1 if it sees a left parenthesis, then it halts saying a no. I am sorry, if it sees if it sees that means number of right parentheses is more. Now, what will happen if you have more left parentheses? Suppose I take an input like this. I have something like this. How will the machine work? It will change this into x, move left, change this into x, move right, change this into x, move left, change this into x, move right, change this into x, move left, change this into x, and move right. When it sees a that means there are no more right parentheses. So, it will go to Q2 and in Q2 it will start moving left. When in Q2 it sees a left parenthesis means there are more left parentheses. So, delta of Q2 left parenthesis is halt, right. So, this is the mapping for the Turing machine. So, this Turing machine finds out whether a given string of parentheses is well formed or not. If it is well formed, it prints a yes. If it is not well formed, it prints a no. But where is that n printed? Yes will be printed here, right. If there are more right parentheses, no will be printed here. If there are more left parentheses, no is printed here, right. It is not printed here, it is printed here. You can slightly modify the machine and make it printed there, does not matter, just make it move and find print it. Let us consider one more string and see how the parenthesis checker works on this string. This is the given string and it starts on this symbol in state Q0, the left parenthesis, and it uses this mapping and moves right in state Q0. So, the next ID becomes this. In state Q0 it sees a right parenthesis and changes that into a x and goes to state Q1 and moves left. It uses this mapping and so it prints a x in this place and moves left in state q1. So, this is the next ID, and in q1 it sees a left parenthesis, it changes that into a x using this mapping and starts moving right in state q0. So, this becomes the next ID, and from this ID it reads the x and just moves right, and it moves right in state q0 looking for the next right parenthesis. These are just right moving, and here it just moves right using this mapping, and this is the next ID, and from this ID it changes the right parenthesis into x and starts moving left. The mapping used is this, and it moves left in state q1. Now, in state q1 it sees a left parenthesis, using this mapping it changes that into a x and starts moving right, and it starts moving right till it sees the next right parenthesis. So, now in state q0 it sees a right parenthesis, it changes that into a x using this mapping and moves left in state q1, and here it reads the left parenthesis and makes use of this move and changes that into a x. Again it moves right looking for the next right parenthesis and changes that into a x using this move, starts moving left looking for the matching left parenthesis. So, these are left moving moves, and it moves left until it sees the matching left parenthesis. Now, here it sees the left parenthesis is state q1, changes that into a x using this move, then starts moving right. It keeps on moving right in state q0 until it sees the end marker A, and it encounters A in state q0. Now, when it encounters A in q0, that means it has seen all right parentheses, there are no more right parentheses left. So, it has to check whether there are no more left parentheses. It goes to q2 and keeps on moving left looking for a left parenthesis. If there is no left parenthesis and it reaches the end marker A in state q2, that means it has matched all the right and the left parenthesis, and so it prints a S. At this stage it prints a S here, telling us that the given string is a well formed string of parentheses. Now, what happens when you have more left parenthesis or when you have more right parenthesis? Look at this case where you have 2 left parentheses and 1 right parenthesis, you have 1 more left parenthesis. So, how does the machine work? It moves right looking for the right parenthesis and changes that into x, moves left looking for the matching left parenthesis, changes into x and moves right. Now, in q0 it sees a, that means it has exhausted all the right parentheses. It moves left in state q2 looking for the A. It has to reach the A in state q2, whereas it encounters a left parenthesis in state q2, that means there are more left parentheses, and so it prints a no, telling us that the given string is not a proper string. Now, this no is printed in the place where you have more left parentheses, whereas the S was printed at this position. Now, what happens when you have more right parentheses? So, this is a given string where you have more right parentheses. Let us see how the machine works on this. it starts moving right, looking for the first right parenthesis, changes that into x, moves left, and then changes the left parenthesis into x, moves right, and then changes this into x and moves left in state q1. In state q1, when it is moving left, it is looking for the matching left parenthesis, but it does not find one. It reaches the a in state q1, that means there are no matching right left parenthesis for the right parenthesis changed last. So, it prints a no at this position, making use of this move, it prints a no here. Note that when there are more right parentheses, the no is printed at this position. When there are more left parentheses, the no is printed wherever you find more left parentheses, and when the given string is a proper string, S is printed in this position. So, now you know how to construct a Turing machine for certain purposes. So, we can consider some more example. As a homework, you can take this. Please try this and come for the next class, which is given a Turing machine. It contains the, see, the input has to be like this. Input is, this is all blank, blank, blank. Some unary number is given. Unary to binary converter. The unary number is given here, and ultimately the answer has to be given here, the binary number. What is this? 8, no? So, you should have 1000, but in here you can put it as B A, something like that. Print here, where A corresponds to 0, B corresponds to 1. Given a unary number here, this is all blank, sorry. Ultimately, the binary number corresponding to that will be printed here, but instead of using 1 and 0, you will use B and A to distinguish between this one and the other one. You can use 1 0 1 also, does not matter, but convenience sake you can do that. Try to do this, and the reverse direction also you can do. Given a binary number as the input, design a Turing machine which will ultimately end up with a unary number for that. So, these two you try, and we shall discuss them in the next lecture.